Hi guys, I'm Liviu Ivanescu. Welcome back to our webinar series. Today I'd like to introduce you to the smart power grid world. Here at the Optical Zeitgeist Laboratory, we're investigating energy management aspects, targeting the reduction or the shift of the load. We need therefore to know which ones can be reduced and which ones can be shifted. The National Electric Company in the UK offers real-time access to the power consumption at the national scale, at 30 minutes time frame. In order to particularly emphasize the residential component, there are only few individual studies done at low temporal resolution, like 15 minutes, and the broken down contribution to the individual appliances is not identified, particularly human component. It appears, therefore, to be a lack of analysis of the real-world customer behavior. There are mainly two unknowns: user behavior and the actual energy consumption, which can differ from the specification. I'm going to share with you the experience my colleague Shin and I earned by measuring real-world energy traces containing both loads unknown as. We recorded for a few weeks energy traces for three distinct types of individual appliances: a printer, two microwaves, and two refrigerators, as well as global energy traces for a 24-apartment building. There were, in our opinion, good candidates for smart grid research, such as household load scheduling. We realized that we need to record traces at high temporal resolution, less than 10 seconds. This is the time scale for the use of a printer, a microwave, opening the door of a refrigerator, etc. We achieved such resolution by using current cost NV home energy monitors, providing 6 seconds live sampling. We have here the transmitter, the Zigbee transmitter, the current probes, and the display providing the link with the laptop, the receiver. For related parameters behaving on longer time scales, like temperature evolution inside refrigerators, we used sensors from the Crossbow MEMSIC EcoWizard energy monitoring system, providing 1 minute averages. Both systems are Zigbee based. So these are the sensors with the Zigbee transmitter. We have probes, and this is the base station with a USB connection to upload the data to the laptop. I shall also introduce you to the North American energy distribution system. The electric energy comes from the utility to homes and offices by two hot legs, meaning 220 volts AC phases, in antiphase with each other. Between the two phases, one can then have 240 volts, generally used for electrical cookers and ovens. Most of the load is, however, 120 volts based, and it should be well balanced between the two phases. The magnetic probes we use here to measure electric energy need to be attached around one hot leg only, not the null. The probe magnetic ring has to be very well closed, otherwise a part of the energy to be sent is lost. For example, let's take a look at the power cord. We need to know precisely which is the hot leg, and then attach the probe only that leg only, as tightly as possible, eventually even tire up. Okay, now let's take a look at our measurement setup. Here is our energy trace printer, which is shared by students and professors in this university environment. In order to trace the two microwaves for load, the sensors are dissimulated as much as possible to avoid affecting the user comfort. Concerning the two refrigerators, we have a dedicated temperature sensor having two probes, one in each refrigerator. One here and one there. We simulated as much as possible for the user comfort. We have as well on one refrigerator a multi-sensor, light, humidity, temperature, sending the data wirelessly as well. Behind the two refrigerators on the power cord, we have similar energy tracing setup as for the microwave. The laptop recording the traces is located in the office beyond this wall. One needs to be as close as possible to avoid losing samples. We want to investigate the human behavior not only concerning one appliance, but also identify any correlation between appliances based on the human behavior. For example, one may expect that after opening the door of the refrigerator to take some food, one may use the microwave. At the same time, the refrigerator may start a new cooling cycle. Okay, this is all for the individual appliances. Now let's see our setup at the 24 apartment building. This is the power distribution panel of the building and the view of the setup inside. The recording laptop is located in a room nearby. Okay, now let me show you some insights of our results.
Our fast time series at 6 seconds resolution allow to identify most of the energy consumption features of the real-world appliances. We present energy traces as their power equivalent, meaning energy over time, which is more appropriate for displaying time evolution. For example, in this case of the 25 apartment building, one notices that the load on the two phases is slightly unbalanced. We may eventually want to fix it by a better power distribution. Unexpectedly, one also recorded few sporadic, very high loads, probably due to an appliance malfunction or an electrical short. The averages, on the other hand, emphasize the human behavior, particularly identifying the daily or weekly pattern. Concerning the printer, the time series identified two standby modes. The higher one, active for about an hour after a new printout, was not mentioned in the specifications. The human pattern of the consumption is a characteristic of the summertime period at university. Here, for each refrigerator, we have superposed the power traces of the two microwaves, as well as the temperature recordings inside the refrigerator and the multi-sensor, temperature, humidity, light, for one refrigerator only. Concerning the device behavior, it was unexpected to identify a very sharp and high load at the spin-up of the compressor at the beginning of the refrigerator cooling cycle, which actually was not mentioned in the specifications. For the smart grid perspective, we may want, for example, to shift this peak to avoid having it on the same time with the use of the microwaves. One can as well identify when the refrigerator door opens from the power sensors, as they work at 6 seconds sampling. Temperature and especially the humidity sensors react as well to that event, even on 1 minute averages. The light sensor, however, fails sometimes to identify it. The correlation in the use of the refrigerator and microwave is obvious. Open the refrigerator door to fetch some food and then use the microwave. For example, solely based on correlations, one could switch off the refrigerator for a few minutes after opening its door to avoid simultaneous load with the microwave. We realized, however, that for the office or home environment, the gain in energy or costs obtained by any optimization scheme will be very limited. The human interaction with the refrigerators rises up the temperature inside, meaning longer power on periods at the lunchtime and some perturbation of the regular cooling cycle in the mornings and evenings. From the temperature evolution behavior, one can conclude that the refrigerators could afford being 2-3 hours off. Looking now on those aspects in the averages, the human behavior suggests that we may switch off refrigerators between 12 and 2:30 p.m. while there is a microwave peak in order to shift some load. We recorded the raw data as comma-separated value files. Their name self-explains the content. In this example, the file refers to the raw trace data for the 25 apartment building concerning the phase number 1 only, which is one of the two hot legs, while the columns inside mean the date, the time, and the power in kilowatts.
Okay, I hope that you learned something from this webinar and open you up to the possibilities offered by the real-world traces. Since they offer both human behavior and the actual appliance energy consumption, our trace results can be used as a case study in the research of new household load scheduling schemes. I would welcome you then to use our traces by following the link near this video. Thank you, and I hope to see you soon.